Thanks for joining me in this tutorial to create a subtractive synthesizer in MetaSound. Some recommended prerequisites would be ideally that you have some experience using MetaSounds before, and then hopefully you've worked with synthesizers and perhaps even done some compositional music production with MIDI. So I hope that you're able to learn some basic synthesis methodologies, specifically subtractive synthesis. We're going to learn how to implement those subtractive synthesis methodologies in MetaSound. And then ideally, we're able to make your own patch with the subtractive synthesizers that's effective, it's convincing, and then you can use that in any application you want in Unreal. Now, the core of a synthesizer is going to be a series of modules that are configured in different ways. And because of the modular nature of MetaSounds, we could configure our synthesizer in just about any way you can imagine. But today we're going to recreate a classic approach to using oscillators, filters, and a VCA or an amplifier to shape the overall sound. On the left here, we see our basic sound generators. We have an example here of two oscillators and a noise source being combined in a mixer. And then we have an example here of a filter subtracting or carving away harmonic content, and then an amplifier to decide when and how loud sounds might come out of the system. That shows our audio signal path. Down here we have our control signal path, where we can control different aspects of these functions through typically a different type of signal. So in this case, an envelope might control the filter, or an amplifier, or an LFO might control the filter or an amplifier. So three basic wave types that we might find useful in subtractive synthesis might be the triangle wave, which creates soft odd harmonic series, a square wave, which creates bright and significantly powerful odd harmonics, and then the sawtooth wave, which creates both odd and even harmonics in a bright and powerful way. It's important to realize that in subtractive synthesis, we're creating a combination of rich harmonic content with those oscillators we just saw in the last graph, and then we use a filter to carve away the sound that we want, to create the shape of the sound by moving our filter cutoff frequency up and down across the spectrum. And that movement is created through use of envelopes. Our envelopes are directing things like our filter, directing things like our amplitude to shape that sound over time to create an interesting musical gesture. Combining these simple but profoundly important aspects of synthesis together in meaningful ways, and then learning to adjust each of these parameters very carefully to design the sounds that you hope to achieve will be a lifetime of possibility as you get into the adventure of using analog style subtractive synthesis. Okay, now that we've talked about subtractive synthesis from the theoretical point of view, I think it's important that we go ahead and audition the four primary waveform types that we would run into and use in subtractive synthesis for musical synthesizers. We have four tonal type of waveforms that we would typically run into, and then we have a noise source. Those are the classic ones that are available to us in the MetaSound source programming environment. There are a few more exotic and certainly other types of waveforms that we could be using for sound synthesis, but again, these are the classics that we would run into in traditional subtractive synthesis. So I've already built this quick demo with our four waveforms plus noise. We would of course find those under functions, and under generators we could look up each of the ones that we're using here. Okay, so we're going to start with a sine wave. Sine wave is the least interesting of the four types of waveforms that we would work with. It's the least helpful as far as subtractive synthesis because it just doesn't generate harmonic content. It only has the fundamental. Now, sine waves would have originally been available in test equipment for early radio transmissions. It would have been available in laboratory scenarios for scientific evaluation and testing needs for hearing and other sorts of necessities. There are some interesting experimental precedents where these sine wave generators move from the laboratory to performance in experimental music, but eventually it arrives as a full-on useful tool with Moog Modular and some other earlier types of electronic instruments. So let's look at the sine wave. Let's audition it really quickly. I have turned down the amplitude of this particular one because the way I'm recording this demonstration is just going to be easier for everyone if I keep this down pretty low and I can keep talking. So we don't see a huge amount of peak here in our meter. And down here we do see an oscillator, or an oscilloscope, I should say, excuse me. An oscilloscope measures the oscillations, and we would see a nice sinusoidal wave if my amplitude were higher in this area. And down here we get a spectrograph. What I would like to do is go ahead and add a spectrogram, and that's going to give us a view of frequency over time. So this is frequency over amplitude over frequency. This is going to give me a frequency over time, and that's going to be useful for seeing harmonic content. So if I hit play and we audition the sine wave, most of you that might be watching this type of demonstration have heard a sine wave before. It's the least interesting. It's pretty annoying in a lot of cases. But we can look at that in a third-party spectrogram here, and we see this bar. Again, it's not particularly interesting, but when we get to the other waveforms, we'll see a lot more information about this harmonic content. I really like Insight from Isotope as a tool for demonstrating and teaching about harmonic content. And there you go. The sine wave is right there across this position. Now I'm going to turn the frequency of the sine wave from a 440 up to an 880. I'm going to move it an octave up, and we're going to see that that spectrogram mark move up to a higher position. So I'll do that here. I'll type in 880 for frequency. I'll start and trigger that again, and now we can see that the harmonic content has jumped up higher. So as we change frequency, it's going to be moving from left to right, from low frequency to high frequency. That's how this spectrogram works. And the main thing to take away is there is no harmonic content. It's just a single line here, and the least useful of all of our oscillators available to us. Okay? So now let's jump over and listen to the triangle wave. This is the waveform that is the next most complex sound from a sine wave. I'm going to hold down Control and it's going to move this output to the new pin here. And we'll audition a triangle wave. What is a triangle wave? It doesn't have a lot more going for it than a sine wave. However, it does have some harmonic content. We see a harmonic series, we see overtones, we hear overtones, but they're just not very powerful. So they can be subtle. The triangle wave is a good subtle tool for certain subtractive synthesis. But it still doesn't have the kind of presence and harmonic richness that our other waveforms provide for us. A thing to remember with a triangle wave is that it is only odd harmonics. That came up before, and we're repeating it now. Only odd harmonics with the triangle. So we can see and hear a little bit more harmonic content. We see some lines above us in this version of a spectrogram. It seems a little bit louder, but not particularly louder. And again, here, if we're looking at it from this other spectrogram's perspective, we're going to see those harmonics. We're going to see those other harmonic contents available only at odd integer intervals from the original fundamental. Okay, great. So now we will go to the next most harmonically complex, and that would be our square wave. Now this one is going to seem significantly brighter, significantly louder. Psychoacoustically, it's going to seem louder than the triangle wave. And it only generates odd harmonics, again, just like the triangle wave. However, they have a lot more amplitude. The harmonic content of the square wave is significantly more robust, and that's going to seem brighter here into our ears. It's going to seem louder. We see those harmonic contents available here. And if I look at the other spectrogram, nice, rich harmonic content from the square wave. Only odd harmonics. Okay, now we're going to move to the sawtooth wave. So I'm going to grab the output pin here and grab that down with control click. Back with the square wave. I should mention that it has a unique property available to us called pulse width. We can change the pulse width of the square wave, and that's the balance of the waveform above the zero threshold. So if I adjust that while it's playing, you can hear a shift in the harmonic content. It doesn't change the harmonic content from odd to even or anything like that. It's always going to be odd. But which odd harmonics are being exaggerated or emphasized, it changes with the pulse width. So it's actually a comb filtering effect for any of you familiar with that technology or terminology, and we can hear that with a pulse width. And if we pull up the other spectrograph, you can see some of those shifts in time if we were looking at it from there. Okay, so pulse width is not particularly interesting as a static parameter, and it doesn't sound very good when I'm manipulating with the mouse in this interface. It sounds kind of glitchy, I guess you might say. But when we hook up an LFO, or when we use an LFO as a modulation for pulse width on a square wave, it can really provide a rich modulation source and add some depth to the sound that we wouldn't get from just a static square wave. So we'll look at that in the other patch that we'll build a little bit later. We'll have a pulse width modulation LFO happening on our square wave, and that'll add some depth to the sound, and will add some acoustic interest. Okay, so we're going to move here to the next sound, and this is our sawtooth wave. Sawtooth wave is not going to have pulse width available to us. It's just going to generate a traditional sawtooth shape. Over the years, there have been lots of variations on what type of sawtooth, what shape they are, and how that changes the harmonic content. This one's pretty straightforward here in MetaSound. I'll audition this. This is the brightest of all. This is the sound that has the most harmonic content, the richest harmonic content for us to work with. It's loud. All of the harmonics have significant amplitude. The overtones are bright. Additionally, it's both even and odd harmonics available. So the square wave only had odd harmonics. Some people attribute odd harmonics to a hollow sound. With the sawtooth wave, we're going to get both odd and even harmonics. So it seems to be the most rich of all of the waveforms that we've auditioned so far. It's going to also seem louder, so I'll audition that for a second. And if we look at the other harmonics, we see rich harmonic content, and we see all of those overtones being emphasized here in our sawtooth. So when I'm building subtractive patches that have a rich flavor and have some musical interest and can grab my attention and can really help me express what I'm trying to go for musically, sawtooth and square are my go-to starting places especially for teaching subtractive synthesis. So we get an ear for how the filter is actually interacting with the waveforms and shaping them in useful ways. A noise source is certainly an original part of the vocabulary of traditional subtractive synthesis. You can add them with these oscillators to more traditional voicings for like a flute. Because of the aperture and the way we blow on a flute, having a noise source would be a great way of imitating the friction of air passing over the flute's aperture, in addition to the tonal elements of the flute's body. But it can be a little hard to make useful in the context of a lot of subtractive synthesis patches. That's going to be a matter of taste, whether you add them to your own tonal type patches, but they're very useful if you get into and try to implement some percussive sounds. So if we want to make a hi-hat sound, very easy to do with a nice bright white noise source. And in that case, I might use a high pass filter rather than the low pass filter that we typically start with in subtractive synthesis. We could have hours and hours of demonstration of just creating percussion sounds with traditional synthesis techniques, but we're just going to play the noise source now for reference and move on. And of course, this is a randomly distributed amplitude. So we have all frequencies at all amplitudes at in all phase. So all frequencies at the same amplitude but all different phases. That gives us a random wave pattern. And if we look at that in a spectrogram, there's no pattern to be found. Okay, so for what it's worth, the noise generator in MetaSounds, we have two choices, pink noise and white noise. Pink noise is great for imitating or shaping the noise to closer to the way we hear sounds according to an equal loudness curve. It sounds more balanced. White noise is technically pure, and again, pretty good for creating some of those percussion sounds that I talked about. Okay, so we have two noise shapes or spectral shapes, pink noise and white noise. All right, that is it for going over these oscillator sound source types that are available in MetaSounds. These are the core building blocks for creating our subtractive synthesizer. So we'll move from this to actually building out our patch so that we can use these in combination with the other modules to turn these into something a lot more interesting and a lot more engaging than just pure waveforms. Okay, now that we've learned about the basic waveforms that we might run into and use in a subtractive synthesis patch, now we want to look at an overall patch. We'll get a sense of where we're headed. Hopefully this will inspire folks to design your own subtractive synthesis patches that are going to be integrated into great gameplay or whatever other implementations you might have. I was really thrilled that with the tool sets that have been provided for us that I'm able to get really close to some of the sounds that I've been designing and searching for, both on classic analog synthesizers, vintage equipment, modern equipment, and then a lot of traditional soft synthesizers that a lot of folks work with today. Again, there are lots of different synthesis methodologies out there that are available. There are lots of different approaches to subtractive synthesis, but this is the classic one that we've seen in early, some people would call it our East Coast synthesis, subtractive synthesis. It's generally a Moog style synthesis that was adapted also by several other synthesis manufacturers. ARP takes a very similar approach with the ARP 2600 and the main modules that are available. And then we see a lot of Japanese musical synthesizers adapting the same approach. And that approach, as we talked about earlier, primarily is constructed with a bank of oscillators, a mixer, which combines those oscillators together for signal, and then a filter that shapes that sound. And the filter is controlled by envelopes. And then at the end of the signal chain for the instrument itself, we have a VCA, or a way of controlling loudness. When I began my work in early synthesis, I thought the VCA was pretty important for shaping the character of the sound. And to a degree, I still believe that, and that's true. But I feel now, having spent a lot more time with these synthesizers, the filter is where most of this work is happening in subtractive synthesis. So 80% of the character of the sound from subtractive synthesis happens in the filter. We'll talk about the filter, we'll get there, we'll make some choices and make some adjustments to the envelope. But before we do that, we're going to start working with our core oscillators at the beginning of the patch here, or earlier in the patch. So I am going to keep our audio signal more or less heading up here on the top row, and then we'll have our control signal down here a little bit lower on a different row, so that we can think of the modulation sources as maybe a little bit separate than the actual audio path. And that's something that I think is important when you're working with these type of systems, especially modular systems where you can connect so many different parts together, to keep your audio path, where the sound is actually coming through the system, separate from, at least cognitively or conceptually separate from, our control systems. So I guess you could call this MIDI player over here another control system. So maybe in that scheme of things it'd be a little bit better down here, but we're going to leave it up here now for visual organization purposes. Okay, so we're going to I'll show you how to build a MIDI player. In this particular patch, I've got a simple arpeggiator, arpeggio sequence loaded. It's a 2-bar sequence, I think, repeating. It's a MIDI file I generated in Ableton Live and exported as a clip and loaded into one of these modules. We'll build that together a little bit later, but for now, when we press play here or start the MetaSound, when we audition it here, that's going to give me a trigger to start this sequence, 2-bar sequence playing, and it's going to loop it. That's going to send control data out to our envelopes, which will open up our voice over time, and simultaneously we're going to extract pitch information and tell our oscillators which pitch to play. Okay, so I'll go ahead and start this here. Okay, and we'll work our way through the patch. We can see the MIDI sequencer coming out here, being turned into MIDI note triggers, note on, note off, and those are going to our envelopes. We have one envelope for a filter and one envelope for amplitude. The same module is giving us our MIDI note number, and you can see that changing as the pattern changes. And those MIDI note numbers are getting converted to hertz in a MIDI to frequency conversion module. And then we see the oscillators that I put together for this patch. So in this patch here, in particular, I chose to have 2 sawtooth and 1 square wave. So 3 oscillators, again, a classic configuration. We could get away with 2. A lot of great synthesizers out there had 2 oscillators with some LFOs or some other variations. We could get away with 1, but it's really difficult to make interesting or sonically rich patches with 1 oscillator. Having 3 is pretty great. That's a great place to be, especially when we have plenty of opportunities to build this ourselves and aren't limited to hardware specifications. So I picked 2 sawtooth and 1 square, and I think of this top oscillator as my primary oscillator, oscillator 1. And then we can decide which of these or how much of each of these proportionately are mixed together. So we have 3 different gain knobs for my 3 different oscillators, and those are going and controlling this mixer. So oscillator 1 feeds into the input here, oscillator 2, another sawtooth feeds in this input, and so on with the square wave into here. We talked a little bit earlier about changing the pulse width, and what I have here is an LFO changing the pulse width very gradually. When we build this together, I think I'm going to use a simpler LFO than the one I chose here, but this one sounds pretty good in the context, works pretty well, but it required a little extra programming that we could skip when we do this together. Let's see. Here, there's an important part of this ability to work with oscillators that was available when Bob Moog and instrument designers got together and really created the first musical synthesizer as we know it. Having the ability to offset our oscillators by octaves is really important. This is something we might see in an additive synthesizer like a pipe organ. We pull out different stops to open up bigger pipes and create different harmonic content. So here we could quickly, on a Moog oscillator, we could jump around to different octaves. So I built that in here as the ability to switch our octaves on the fly. So it's easy for us to design a voice by changing the octave or offsets of each of these. And you'll hear that in a moment, how that works. Another aspect that's really important is being able to detune an oscillator. So on oscillator 2 and 3, I have the ability to detune them or put them slightly out of tune. This is especially important in digital formats when oscillators can be perfectly in tune. That was much more difficult to achieve in analog oscillators, VCOs that were controlled by voltages. It was difficult to get them perfectly in tune with each other and to track perfectly over the range of a keyboard. But in the digital system, they do that perfectly so well that it's a problem. Having the waveforms perfectly in tune is less interesting than having them slightly out of tune. I think of this as maybe a row of string players on in an orchestra, right? We have several instruments playing the same melody, and the fact that no one's ever going to play exactly the same pitch creates an interesting and rich modulation, slight intermodulation between the voices. So by detuning our oscillator slightly, that adds a significant amount of interest to the voice. Okay, so we can hear that effect if I bring down the amplitude of the other two oscillators, and we'll just listen to one. I'll play it one. We're just hearing one oscillator. We're hearing this sawtooth coming into the mixer, okay? Now, I do have some reverb at the end. I'll talk a little bit later about why I think that's so important. So I'm going to bypass the reverb right here for now so we can go back and hear this a little more clearly. One oscillator. Now, as I mix in the second one, I'm going to turn off the detuning. So I'm going to make them in tune. I'm going to bring up and I'm actually going to make them the same, playing the same note. So I'm going to change the octave offset to 0. There's no detuning, and as I bring in the second oscillator, which is identical to the first, really, you get a little bit of phasing because they're not perfectly in tune. They're not perfectly in sync. But there's nothing really interesting happening between the two working together. Now we could make that more interesting by changing the octave, but if I just detune it a little bit, already we have a more interesting sound. Now we go too far, right? If you go too far in your detuning, it sounds pretty strange. That can be used aesthetically in certain contexts, but with just a little bit of detuning, we can add a lot of harmonic interest to our oscillator. So I think this is an important feature to add to a system like this that we've got here in MetaSound sources. In other software synthesizers, there'd be a knob here that would say detuning. Maybe we'll see that as a feature in these different wave shapes in the future, these modules. But we can certainly, because this is a modular system and based on simple math, we can add a little bit of value to offset this pitch that's coming here. We can change a little bit, detune these two oscillators. That creates a more interesting harmonic content. I'll play that one more time, and we'll pull up the other spectrogram so we can see that together. So there's going to be some push and pull in the harmonic content over time. So the shape that we're seeing undulating is going to be more pronounced with different detuning. Okay, so that's a matter of taste as how far you want to go. The other thing that we can do with these oscillators is shift them by different octaves. So I'm going to move this up 12 semitones. And just based on some of the limitations of this particular setup and system, having semitones here is instead of an octave switch is certainly easier to implement. It does give you some other opportunities too. Instead of tuning them to different octaves, we could also tune them to different intervals. So we could have this one as a fifth. I'm going to leave it as an octave right now. And you can hear that brighter sound come in, right? So we're adding the brighter sound, the higher octave sound, on top of the first. Now again, a classic approach to this would be, well, I'm not going to move it by a whole octave. If I go 7 semitones, that would be moving at a perfect fifth from the original. Whatever note the original is playing, the main oscillator is playing. This oscillator is going to be 7 semitones above. And that creates a nice harmony that you may want to experiment with. Okay, so I'm going to leave this back at 12, 1 octave for now, and then we'll keep moving. So down here on the third oscillator, it's a square wave, so we do have that opportunity for pulse width modulation. I'm going to do some detuning again, but this one I'm going to drop down 12 semitones, so it'll be an octave below. So this will be like a sub oscillator to some degree. And then I'll drop it down 12 semitones, excuse me, negative 12. So that's adding some bass content that we didn't have before and makes for a more rich sound. And now we can mix these in different proportions. Okay, it sounded pretty good. 3 oscillators, a classic approach. I like 2 saws and a square. You could take a different approach. We could have 3 sawtooth. We could have a sawtooth and a square as 2. But having the 2 different wave shapes gives you some good opportunity, especially if you take advantage of the LFO modulating pulse width. There can be some rich sounds that come out of that. Certainly having a triangle wave is useful, but you're going to have to choose the way it interacts with the filter more carefully. Now in this patch, we're using a ladder filter. This is, again, I would say 80% of where the real sound of this voice comes from. The ladder filter is, again, from Moog's patented design of the transistor ladder low-pass filter. You can use them in a high-pass configuration, but low-pass filter is what we're going to hear and use most often for any type of patch that we'd hear in a traditional synthesis voicing for leads and bass lines or anything like that. We've got this ladder filter here. We can't even change this one from a high pass or low pass to a high pass. This is going to be a low pass filter. And almost certainly this is going to be a 4-pole filter, which means that's going to be 24 decibel per octave cutoff rate. So that's going to be a steep cutoff rate versus the other filter type that we'll look at in a moment, which will be softer at a 2-pole or as 12 decibel per octave shape to the filter. So here's our filter, and we do have a graph of what the filter shape will look like. And resonance, as we talked about earlier when we were looking at the kind of synthesis theory, resonance is an important aspect to work with. Again, that's a matter of taste, where you're going to use resonance and how strongly, what type of voicing that's going to be useful in. With really strong resonance, the resonance itself can take over the melodic work you're trying to achieve. So you have to be, if it's a melody line, then you have to find the right balance of resonance in the sound, as it's going to emphasize a different frequency than you might be trying to play with the melody. But having a sum is almost always a good choice to start with. Adding more is going to be a matter of taste in your voicing. Okay. Another really important aspect of working with filters is the amount of effect that the envelope has on the filter. So I built a amplifier here, or a gain stage is what I would call it. It gives me the ability to adjust how strong the amplitudes modulation is on the filter's effect. So we'll hear that as we start to balance our use of the envelopes. Okay, so the filter envelope is here. The amplitude or the loudness envelope is here. I could talk about this for half an hour, another half an hour about how these two interact with each other. And then you'd think I could talk about that with the loudness as well. But again, I really believe that most of the design work happens in the filter envelope. And the amplitude envelope is just there to make sure we don't have a note playing forever when we've stopped triggering the voice on the keyboard or whatever the sound source is. It's kind of more like a gate that makes sure that your loudness is just not coming out. Now, if you're working with something like a sine wave or a noise source or maybe even a triangle wave, you could do a lot of work without even having a filter or filter envelope, and you could do all that work with the amplitude envelope. But when we're doing subtractive synthesis, rich harmonic content coming from our oscillators, this is really happening in the filters envelope. Now, I built out controls for our traditional attack, decay, sustain, and release times. I'm taking a shortcut in our patch today, and I'm connecting these controls to both envelopes. Ideally, we'd have completely separate control of both of these, but again, since most of the work's happening here, and to make this, this tutorial a little more straightforward, I've connected these controls to both of them. So in some ways, it essentially is one envelope controlling both these sources. And that was a solution that some hardware synthesizers certainly used. But let's work with that a little bit. So if I adjust the attack time, we'll hear the softer filter work coming in. We can create a sharper transient by reducing our sustain level. And finding the nice relationship between the attack time and the decay time. So this would be more like a pluck, a pizzicato pluck or something like that, and maybe a little more percussive. Or we could soften that up again. Okay. Now as I go up here, working with the filter again, if we increase that resonance, you can see the filter moving. Some of that shape over time becomes more pronounced. Maybe not useful, but certainly you can hear the effect of resonance working on this. Now I'm going to adjust the amplitude of the envelope affecting the envelope, the filter. So this can soften the approach, and having a lower amplitude might be great for certain voicing in a lower register or a bass-based sound. Or we can really open that up for higher frequency content. And you can see that spectral content really opening up here versus being more choked or muted here. And this is interactive with our shapes. So I find the relationship between the envelope and the filter and this amplitude parameter really important, that you spend some time building, in this case, building the tool so that we can experiment with it, but then taking the time to experiment with different relationships between the amplitude shape of the envelope and the amount that we're allowing that to pass through to the filter's control system. So spend some time developing that, and then that's going to help you be a better sound designer for the synthesizer voicings in MetaSound. Okay, and lastly, we have a VCA. That's just in my mind is more like a gate here at the end of the process, making sure that we're not letting sound leak out when we're playing, or we're not playing this or triggering the sound. And then I think it's important for us to have reverb in just about any synthesis context. It could be very light, but I think it's really important to give a little bit of acoustic space to electronic instruments so they don't sound completely in the box. It sounds more in place in an environment, and usually adds a tremendous amount of interest to the sound. And we have a plate reverb here, which is available in MetaSounds. That's the only reverb available directly that I'm finding useful in this context, and I've fine-tuned a few of the features here we'll do together. Okay, so that concludes our walkthrough for what might inspire you to work on this, and then we will build this patch together. Okay, now that we had an overview and hopefully something a little inspiring to work towards, let's build our MetaSound Subtractive Synth patch together. So I'm in a basic project. It is actually important to note that we need to load a plugin to make this work. As so many things we have to do in Unreal, we've got to make sure we have the proper plugins loaded. So under Edit, I'm going to go to Plugins, and I'm going to make sure that we have the Harmonics plugin available, and this will open up all of the modules available to us in the demo that I'm giving, and certainly in this tutorial. So make sure that you've got this this plugin enabled and allow Unreal to restart. And other than that, I just obviously have a pretty basic project here. We're not going to be working in the outliner at all in an actual level. We're just going to be working in MetaSound patches today. So we need to create a new MetaSound source. Under Content, I've created a subfolder called Audio, and I've already done, this is the MIDI file I imported. This is the overview that I gave just a minute ago, and we'll go ahead and create our own MetaSound source to try to recreate this this patch that I showed you. So I'm going to right-click, and under Audio, we've got MetaSound source, and I'm going to type that as an MS MetaSound source. And we are going to call this one Subtractive Synth for now. Okay, great. So I'm going to open up this patch, and here we are. Now, the first thing that we want to do when working with a MetaSound from scratch is, again, as I mentioned earlier in the prerequisites, I am assuming that most of you have some experience working with MetaSound, so I'm not going to go through every possible iteration of what's necessary to know when we get started, but we definitely don't need this on-finish cue, since this is something that might be repeated or used several different times. It's a looping type sound, so we need to remove the one-shot interface so that we don't have to worry about this unfinished node. So I'm deleting that interface so that we are having a looping type sound versus a one-shot sound. We're going to need to make plenty of room between the on play and our output, so I'm zooming out and making plenty of room to work with. And out of all the things to start with, going from left to right in the demo, we had the MIDI player at the beginning, but I want to go ahead and work with our oscillators first. So I'm going to set up our oscillators, our filter, our amplitude controller with the VCA that we talked about, and then an envelope to control those things. And then we'll build the MIDI player to get right back where we were in that demonstration earlier. Okay, so we're going to start with the oscillators. That's the core of our subtractive sound. It's the starting place for our audio path. So let's go ahead and do that. Right-clicking here. I'm going to go with just like we did before, I'm going to go with a sawtooth, and we're not using an LFO sawtooth. We're doing with a generator here. And there's our sawtooth sound source. So we could pass that up the output to prove that it works, but I'm going to trust that we're ready to go with this one. And I'll go ahead and add the next one. And so I'll right-click and duplicate this, this module. So we have two sawtooth waveforms. And then I want to add my square wave as the third primary waveform to work with. So I'll add that down here. And I'm going to like to keep my oscillators on this orientation, top to bottom, 1, 2, and 3 oscillator. I can right-click on, I can click and drag over them, and then I could go to alignment, and then, or I could do a Shift A and make sure they're all lined up nicely from left to right. As we go, I like to keep things fairly clean as we go. And then do my comments a little bit later. So These are going to be 3 audio sources. What do we need to do to combine those? We need a mixer. So I'm typing in mixer for my mixer, and we're definitely doing a mono mixer. Traditional Subtractive synthesizers were mono. There's certainly examples where we can do some really interesting things with stereo voicing. At the filter place, where maybe we have 2 filters and we pan them slightly differently, or add different offsets to the filter cutoff frequencies. Those add some interesting things. The Moog Voyager is a great synthesizer that does that. I'm not imitating that today. We're going to stick with mono audio path all the way up until some effects at the end, some reverb at the end. So we have 3 oscillators we're trying to mix together. I'm going with a mono mixer. So our audio signal is going to be the purple wires here. We're going to wire those in here and here. Okay, so right away we want control over the balance of these 3 oscillators, right? The ratio of how much we're going to listen to one or the other. Let's move this up here so we get a straight line of our audio across the top. Maybe that'll be nice. Maybe keep it like that. And so we want gain control for these. We want 3 dials that we can interact with and control the mixer. So I'm going to right click with this, and I'm going to promote to graph input. Okay, and because that is a float input variable, it automatically flips to this type of control with where we have the slider. If we were trying to do that with an integer, we're going to have to take a couple of extra steps, but thankfully this is ready to go. We right click, and then that can turn into an input. And so sure enough, over here on my panel over here, this knob is called gain 0, and gain 0 is pretty useful as far as a naming convention, but I'm going to go ahead and talk about this in relationship to the oscillator. So I'm going to change the name, pressing F2 to change the name, and I'm going to name it with the oscillator first. So this will be oscillator 1, and this, to me, this is going to be the level for the mix. So instead of gain, that's a little more technical term, we call it oscillator mix, oscillator 1 mix. That's fine. Whatever works for you. You're understanding where that is, I'm sure. So this is a range of 0 to 1. That's zero would be no amplitude, 1 is full amplitude in this signal chain. So that's good. We don't need to make any changes to the range of this knob. 0 to 1 by default is great for that. Okay, we're going to do the same here. We can't copy and paste or duplicate that because that's going to actually create the same input and try to map it to 2 different things. We don't want that. We want a new input. So I'm going to right click here and create a new input, and we're going to call this one OSC2, oscillator 2 mix. And we got to grab that and not get too confused. I'm going to put these next to the oscillators instead of next to the mixer, just so we can kind of keep that visual a little more connected. And of course, we're going to do the same thing for the third, and we'll call this one OSC3, oscillator 3 mix. Does that sound like a good idea? I think it does, and here it goes down there. Okay, so now we can control the loudness of each of these into the mixer, and we'll keep it simple in the beginning by keeping oscillator 1 wired up from the beginning here. Okay. Cool. So what comes next after the mixer? Well, what comes next is the filter. So we're going to drag this out, and we could type in filter, and we do have a state variable filter, or a let's see, yeah, state variable filter, and that would be like the Oberheim SIM, traditionally the Oberheim SIM filter, and that's going to give me a high pass, a low pass, and a couple of other variations, which are pretty interesting, and a great synthesis tool. It's going to be a 2-pole filter instead of the 4-pole ladder filter, which means it's brighter. It allows a little more sound to come through, a little more harmonic content to come through. But we're going to stick with our traditional Moog transistor ladder filter. And there we go. We're right back to where that demonstration patch was. So cutoff frequency at 20,000 hertz is, there's no filter at all. It's not doing anything because that's the highest frequency that we can hear as humans. Now, in analog synthesis, and in our case, since we're emulating this kind of analog synthesis approach, there isn't a lot going on at 20K. There's not a lot going on at 15K. the majority of this stuff happens at 10K and below. So we really want to be focusing on a range much lower than that brightest sound. Where this musicality is happening is usually 10K and below. And obviously we're not trying to cut everything off above that, but that's where the primary voice is happening. And so we'll talk about that and manipulate that later. Here's our resonance parameter. We can go ahead and promote this to a variable or create a graph input, I should say. That'd be a better way of saying that. This is, well, we're just going to leave it at resonance. That's perfectly fine. Resonance is the only parameter for us in that range. We'll have that as our filter resonance. But we do need to change the range of this this dial at this point. So the range of the dial really needs to be a resonance of 0 is fine as a starting point. We probably need to get up to 8 or 10. So I'm just going to go ahead and put 10 in there as our max for the range. So what's the default? You know, we could put that at 0 if you wanted to for the default. That's great, but we would be able to go all the way up to 10 for the resonance if we wanted to. Most of us will be in this range probably to get a good sound that we're looking for. Okay, so I'll go ahead and temporarily attach a input pin to this, and I'll need to remember to delete that so we don't get too many unused inputs over here. But we'll go ahead and use this temporarily. It's by default it's sticking at 20K, so that's great. It's going all the way up. We'll just listen to what this is like now for a moment, okay? Before I do that, I'm going to go to sound source, and I'm going to decrease the amplitude since I'm recording with my voice in real time. I'm going to put that down to about 0.3 so that I'm not blasting your ears with this sound as I'm trying to make this demo recording. And so I'll activate this, and so we'll hear these 3 oscillators coming through, and then we'll just listen to what the filter sounds like on its own. Okay, and then a little resonance. Okay. All right, so let's bring up one of the other oscillators. They're not going to really sound particularly interesting because they have pretty much the same wave shape. We need to do a lot more work before that's going to start sounding interesting. Okay, so our basic structure is working so far. 3 oscillators into a mixer and then to our filter. Now, as you're learning to build these type of patches, it's much easier to go step by step and try to audition your sound as you go. So instead of trying to build every little nuance and then hoping you got everything right, try to keep it simple and make sure that your audio signal is still working, your voice is generally still working, and you're not having to go through and problem solve everything along the way, everything at the end of the process. Doing that along the way is a great compromise. So I'm going to delete this input here. We're not going to use that one. And I'm going to delete it from here so we don't end up with too many unused inputs. Okay, so we need a VCA at the end. The VCA is a module that we would see in a modular system labeled as VCA. For us in this more mathematical approach, which for me was very familiar from what was called Max MSP from Cycling 74 or other graphical programming environments for this type of work. So I'm going to type in multiply. We're really multiplying here. We're multiplying audio, and that seems like a strange idea, but that's what we're going to do. So the original signal is 0 to 1. That's the amplitude of the audio. Okay, and then if we multiply that times 0, we get no amplitude. If we multiply it times 1, then we're getting full amplitude. So it's really an attenuator. It's a VCA, you know, you might even call it an attenuator. It's where we're attenuating the signal rather than actually boosting it. But we'll let that go for now. And so we could hook up a dial to this and combine that with the other things we've done already and hear the amplitude increase, but we're gonna let that go and go ahead and start working on our envelopes, okay? All right, so where would the envelopes be? We can put them wherever we want, but I'm going to put them just generally down here for now, and we'll move them accordingly as we start laying things out. So there are lots of types of envelopes in synthesis history. Some of my favorite are really simple envelopes with just an attack and decay. But if we're going with our classic subtractive synthesis, then an ADSR, or attack, decay, sustain, release, is going to be the most common filter for us to work with. Now we're actually going to need both of these. Audio is going to give us the right type of signal for working with this audio multiplier. So we can see the audio signal here. And so that is a signal type that makes this VCA work easily. So this envelope is generating a shape of audio signal. We're not actually listening to this audio signal. It's being multiplied against this to allow our signal to pass through. So we can leave that like that for now, and we'll go ahead and build the filter envelope, ADSR, and in this case we want a float. So the filter, as you remember, is being controlled by this. This is what we really want to be controlling on the filter, the cutoff frequency. And so since that's a float signal type, then we also need to be sending out a float signal type for here. We can do conversions if we need to, but since we're going to be using these so often, if we're doing a lot of synthesis patching, I think this is the appropriate way to use these envelopes. Use the float for our cutoff frequency, and then to use our this envelope for our amplitude. And I think I'll go ahead and put them like this, top to bottom. And maybe move these out a little bit to the right for now. Okay, and I'm trying to keep that audio path somewhat straight. And then we'll move resonance closer to the filter itself. So really difficult to use these with numeric inputs. It's going to be really awkward to try to type in different values for these parameters and do that in a useful way. So for now, instead of using the sequencer like I did in the demonstration earlier, instead of using the MIDI sequencer playing the arpeggiation, I'm going to go ahead and use our input trigger here and temporarily hook that up to both of my envelopes so that we can trigger this and test it a little bit just to make sure our signal flow is working. Okay. After I hooked up this VCA, we really couldn't hear any of the signal coming through, right? If I hit play, all this audio is coming through, but it's getting blocked by, well, both the filter and the VCA. So we need the envelopes to be working in order to hear any of the signal. So it's going to be much more efficient to go ahead and test our envelopes to see if they're working before hooking up all of the MIDI stuff. So I'm using the input trigger temporarily to trigger my envelopes to test this signal. And if I had a MIDI controller attached and all of that business, I'd probably be testing it with my keyboard at this point. But we're going to go ahead and go with this, and we need to go ahead and build out these control sources. So this is going to be time. So attack is a time source. So we see a different type of data set here for time. And then sustain, even though it's part of the same shape, or we see it on knobs on a synthesizer, it's actually a gain rather than time. So sustain is how loud the sound is when we hold the note. And how long we hold the note is determined by when we release the key on the keyboard or when the note ends in the MIDI sequence. So this is an amplitude rather than a time parameter. And that's really important to remember. I mentioned earlier when looking at the graph, this is amplitude and not time. And you really, as soon as you get your head around that, then a lot of this envelope problems will start to solve themselves, okay? So we're gonna right click on this and we're gonna create a graph input for this, and that should be ready to go, except the default values are not very helpful. So we're gonna need to come back to that and tune these up for default values. So I'm going to go ahead and build these out now. Having difficult grabbing that node. There's my decay. And we'll go ahead and get our sustain sustain amplitude. I made my own mistake there. And then our release time here. Okay, great. So we've got our release time at the bottom. And as you know, in the demonstration earlier, I went ahead and used this for both. I'm taking a shortcut. It'd be better to have individual controls for our amplitude and our filter. But, excuse me, I made a mistake there at the end. This is supposed to go to here, and this is not supposed to be connected to that. And this goes here. Okay, so I think that's about right. I double checked that really quickly visually. That all looks good. And now, before we go too much further, we need to set the default values of these. And I've had difficulty getting exactly what I've wanted with these numbers here. I'd like to have 0.01 as my lowest range on my attack time. On a digital system like this, we never want 0 as our attack time. We're going to hear pops as the oscillator pops open, and amplitude and the filter and so on. So having 0 for your attack time is just generally a bad idea. So I would like to have that at 0.01 so we can never bottom out there. But every time I tried to type in my desired times, it didn't work before, but it seems to be working okay now. So I've got a default of 0.01 as the bottom and 250 milliseconds as the top. And that's pretty good for this type of pattern that I'm going to be working with. If we're working for much longer pad sounds or musical intervals that are much longer, musical notes that are much longer in time, then we'd want a longer range for this, but I'm going to keep it simple for us for right now. And am I going to still 0.01 and then 0.25? Yeah, so it seems that gave me trouble before, but it seems to be okay now. 0 to 1 is perfectly good for sustain. We don't need to change that default setting. And then the same thing for release. I'm going to put in 0, 1, and then 250 milliseconds or 2.25 for that attack time, release time. We'd want more if we had a much slower pattern, but this should be good for us for now. And sure enough, if I go ahead and hit play, I was hoping we would hear some sound. And I have a pretty good idea why we're not hearing anything, but we're not. Okay, so as far as problem solving goes, I already have a problem. I'm getting a trigger. I see my envelope triggering. I see that amplitude coming out here when I trigger my envelope, but no sound's getting through. And visually, I can see a nice healthy signal here, but it's not healthy here. It's in fact it's just not happening. And if we had a really low frequency playback system, you might hear a low frequency sound at this frequency. So the filter is choking off our sound. There is some amplitude there. It's really low frequency, but and low amplitude, but the filter is cutting off too much. So here's our first significant problem. We've got a great envelope, we've got a great filter, but we haven't conditioned or scaled the control signal to work with this. So in more elaborate or more refined tool sets, you might have a knob here that helped me adjust this gain. We'd have a gain stage for how much this is controlling the filter. We just need to build that in ourselves. And I mentioned this earlier in the demonstration. We need to build a multiplier to decide how strong this envelope is going to affect our filter. Right now, it only goes to a small low frequency, and we need to amplify that. So I'm going to right click on this output pin. I'm going to drag away from the output pin. I'm going to type in mult, and we're going to create a mult by float, and we can connect that our output envelope here, and then we need to design that gain ourselves. We need to give this another output pin. So I'm going to go, excuse me, another input source. I apologize. And so this one is going to be filter envelope amount. Okay, so the range, certainly 0 to 1 is not going to work here. I kind of like with this to be ideally like 200 to be like our lowest frequency. It would go down to maybe 100. But the top needs to be, theoretically 20 kilohertz. But for our purposes, putting it at 10,000, like I mentioned earlier, is not too bad. Okay, so if I trigger now, I hear a little bit something coming through, but I really need to increase that gain. So there we go. We're hearing the filter work now. We needed to multiply our envelope value to a higher range so it mapped properly to the input frequency, the cutoff frequency of the filter. Okay, so build in that gain stage for your own patch, and you'll be well on your way to making the filter work in a meaningful way. And this seems like an appropriate approach. There may be an easier or more direct solution that I'm missing, but this is the approach that I found works pretty well. Okay, so this will be a parameter we come back to in the future as we're designing this sound. We've got an input pin for filter amount, how much the filter is affected by the envelope. And that's typically something you find in a synthesizer. It's going to be a parameter readily available for you as part of the design tool. Okay, so this is looking good. We've got our oscillators here. We've got our mixer here. We've got our envelopes here, and then our filter. Okay, I'll go ahead and label this. I'm going to put a comment, and I'm going to name this envelope. I'll just say ADSR. That's going to be self-explanatory. Got our filter here, so a comment. Okay, and not that it really needs it, but we can have our VCA here. So we're following the traditional signal path pretty closely to the documents we've seen before. Okay, awesome. And then our oscillators, right? Okay, so oscillators here, and I'm going to comment those. Actually, before I do that, that's my mistake. I need to, we're going to need to make this box much bigger because we got a lot of work to do with our detuning and so on, and octave offsets. Why don't we go ahead and take that on now? Okay, so we've got our oscillators. We've got them hooked up to the mixer as we would like. We actually wanted the mixer as a separate module, didn't we? Okay, so we need to build out our detuning and oscillator octave offsets. Okay, so I'll need to make room as I go along, and I'll just go ahead and keep going. It would have been nice to wait before I made the comment, but we'll get there a little bit later. Tell you what, let's go ahead and drag these out, delete the comment, and have plenty of room to work with this now. Okay, so the frequency is coming in here, frequency is coming in here, and the frequency is coming in here from our other sources. So we need to, if we're going to do detuning, we don't need to detune the first oscillator, we need to detune the second two. So there's no point in detuning the first one from itself. It's a matter of the relationship between these and the other. So I'm going to drag from here, and we're going to create a multiplier. Okay, And the pitch from our MIDI to pitch converter will come in here. But for now, excuse me, it's not a multiplier. I apologize. We need to create an add. We're not multiplying. We're just simply adding a little bit of value to this pitch coming in here. So the frequency will come in here from our MIDI to frequency input from our MIDI player. But we're going to add with another input. This is going to be OSC1 detune. Okay, so, and what's the range for that? The range for that should be negative, I think about -10 to about 10 hertz. That seems to be a pretty good range for detuning. You could always add more if you felt like you needed that for your personal taste or design. And I made a mistake. This should be oscillator 2 detune. We're not having a oscillator 1 detune. Okay, and then we'll bring in our MIDI to frequency input here, and we're going to do the same here. We're going to drag from here and add float. And we, be nice to copy this, but we would be copying the same input. We need to be bringing this in as a new input, and this one we're going to label oscillator 3 detune. Awesome. And we're going to set that to -10 to 10, our detuning in hertz, and we're adding that to our frequency as that comes in. Okay. Now, we are not going to do the octave offsets until we've converted this into, we're going to do that before this turns from MIDI into frequency. So we actually need 3 modules now, and that's going to be MIDI to frequency. So this is going to be a float for us, MIDI to frequency. So MIDI note numbers are the numbers you'd see on a keyboard. C, middle C is about 60 in a lot of cases. It's the middle of the keyboard, okay? So that needs to be converted to frequency. So that's it's not the most convenient thing to have a MIDI value coming in based on MIDI note numbers and then converting that to hertz. But in many cases, when we're dealing with programming environments like this is a necessary conversion. So that's what we got here. And we can duplicate this one 3 times, or 2 more times rather, to add to this position here. Again, since we're not doing detuning, we don't need that there. And I'm going to duplicate this one more here. And there we go. We've got this input there. So we're ready to start receiving MIDI from the MIDI sequencer, okay? Now, that would be pretty easy to do. It's probably a good idea for us to go ahead and build the MIDI sequencer, test, make sure everything's still working with the detuning, everything else we've done with our envelopes, wire up the MIDI controller to our envelopes, because we really don't want this controlling our envelopes as we had done earlier. Okay, so let's go ahead and build the MIDI side of this patch so that we can start playing our sequence. So I think the core of this is the MIDI player, and that's going to take my MIDI file and play that file from the MIDI information I stored in the file that I load into the MIDI player. So we'll come here, and I'm going to type in MIDI player. And there are a couple of different several different MIDI functions here available. This is the one we want in our case. And we're going to pull down this asset that I dragged into Unreal earlier into my content folder. Earlier I dragged this in after exporting it from Ableton Live. So this is my arpeggiation sequence, and it's going to generate a MIDI stream. And a MIDI stream could have lots of different channels or voices playing at the same time. And it will often have a MIDI clock, which will keep the tempo happening as well. But we have a really simple sequence here, so we're keeping it really simple. I don't need to extract a lot of different types of information from this MIDI stream because the file is only one MIDI channel and a very simple 2-bar loop. So I'll go ahead and loop that. It typically, if your MIDI file has tempo as metadata, I believe the MIDI player should pick up that tempo. In my case, it plays it by the default of 120 beats per minute, or BPM. We need to play it at slower MIDI speed clock, a slower tempo. So we're going to have to bring in another module to change that clock, default clock. Okay, so the MIDI stream is going to come out here. That's the MIDI information that's going to be coming out as though we are playing a MIDI sequencer or playing a keyboard, whatever that might be. And so I need a MIDI note trigger. That's what I need, is a MIDI note trigger. So that's going to take the MIDI note on information and note off information and turn it into triggers which are more appropriate for this type of environment. So MIDI note trigger is right there. Okay. And so the MIDI stream will come in, and anytime we see a note on, we're going to trigger this output here, and anytime that note is released or someone pulled up the key on the keyboard, then we would get a MIDI note off. So we're going to get a note on and a note off trigger every note, at the beginning of the note and the end of the note. What else information do we get out of that MIDI note is the note number, which pitch is actually going to be coming out of the sequence. And then velocity. Velocity is how hard, or technically how fast someone pressed the key if they're recording it on a MIDI controller. A well-made MIDI file will have plenty of great velocity information, but since I wanted to kind of get the feel of a classic analog arpeggiator, analog system arpeggiator, we're not using any velocity information. So that's not really part of this equation. We're just using the MIDI note number and the trigger times, okay? So the note on and note off are going to go to my envelopes down on the bottom, and then the note number is going to go to these the pitch information here. So we're going to take the note number and go here, as we expect. Is that right? Let me double check. Okay, and then MIDI note number here, and then MIDI note number here. Okay, so we'll check and see if that's right. You know, I didn't build this one. Yeah, I think I should have used, let's try this one again here. Let's try MIDI to frequency int. Let's do the integer. That's my mistake. I should have used the integer instead of the float module, so we'll fix that really quickly here. So we don't need these conversions here. I'm going to replace these with this. So we really wanted MIDI note MIDI to frequency integer. That's what we really wanted. We'll fix that mistake here. Okay, so MIDI notes are integers. There's no decimal point to a MIDI note, so having an integer input for this is a better choice than the float input. So I was in a rush earlier, wasn't paying attention to that distinction. This is a better choice, and so now when I wire up the MIDI note number, we don't have that conversion from float to int, right? So there we go, from int to float. So great, we've got MIDI note number coming in to all three of these as we would want. And I'll reconnect this to my 3 oscillators and here. And I think we should be in good shape now for the note values coming from the MIDI note trigger. So again, the MIDI note trigger takes the MIDI stream, the MIDI data coming out of the MIDI player, and it's breaking it down into triggers. I would typically call these gate on, gate off, but we got trigger, note on, note off, and we're going to use that to trigger our envelope, and then of course the MIDI note number we've just distributed to our oscillators for frequency. Okay, so we're going to take note on, and we need to get all the way over to trigger for attack right there. So we're no longer using this. I'm going to alt click this. We are still going to use this module at a different place in the patch, so I'm dragging that out of the way, getting that back over here. Okay, so our input we'll use again later, and I'm taking the MIDI note on to trigger my envelope. Now that's going to be kind of awkward to patch all the way over from there, so what I'm going to do is go ahead and double click here, and we're going to send the same information to both of these envelopes. Okay, so I've got this here, and so what I could do is bring that down and out of the way, and we'll clean this up a little bit later. I'll add another one here, and then I can drag that down. So it's kind of getting out of the way. The signal flow is a little more clean that way, perhaps. And we need to do the same for note off, but that's going to be triggering our note release on our envelope. So like before, I can double click and create a branch node here, and then wire that there, and then I'll just bring this down here so that two of them are together, and then I'll pick a spot and double click, and now I can if you see the little cross bar, you can move this now. There we go. So we got a little bit better flow of the signal coming down visually. We're keeping that data flow separate, and this should be heading in the right direction. We'll double check that now because well, we'll double check that soon because we'll be able to play this MIDI file. Okay, so we've got the MIDI player. I'll double check to make sure we've got the file loaded. That's an important part of this process. And I'll go ahead and you know, I really want to transport. I want to be able to hit play, and just one trigger isn't enough. We've got pause, play, resume, continue. We've got several different things we can go for a transport. So what we really want to do is use a trigger to transport. So we can use our input. When we play this, it will play the transport. So I'm going to drag from here, and I'm going to type in trigger to music transport. And then this can hook up to play. So when we activate the sound, when we play the sound, we're going to get our input trigger. That's going to go to the play function on the transport. That's going to get added to this data set for our MIDI player to play the file. And then the MIDI note trigger is going to interpret the MIDI file into triggers for note on, triggers for note off, and then our actual pitches during each of those interval changes. So I should be able to hit play, and we should be able to hear the sequence play. Okay, great. It's just too fast. And again, that's too fast because this MIDI player did not read any metadata about the original clip. It's supposed to be about 85 beats per minute. So I'd like to be able to just change that here, type in a new tempo here, but unfortunately I'm going to need a separate module to do that. So I'm going to drag from here, and I'm going to pull in a metronome MIDI clock generator. So metronome. Clocks are a really important part of these type of systems if you're going to use sequencers. So having a separate clock module is awesome. I think that's great. Gives us a lot of different flexibility. But in our case, I'm going to hook this transport up to this transport. In this case, I'm really only interested in changing tempo. So our tempo is at 120 by default, of course, and I'm going to lock in at 85. And there we go. Our sequence is playing at the tempo originally intended. And if we wanted to slow down or speed that up, of course we could. Awesome. So the patch is working. Patch is working pretty well. I'm going to come here and adjust this value, see if we're getting any of that kind of good Yeah, subtractive feel. Yeah, absolutely. Our filter's working. I could probably make some adjustments to here and get some expected results. Okay, let's try a little bit of detuning. There we go. So a much better sound as soon as we've detuned these oscillators a little bit. Okay, so you may remember, and we're getting close to wrapping this up, you may remember that I wanted to add octave offsets for all three of these, but I thought it'd be a better idea to go ahead and have our musical information coming in before we did that. So we programmed the detune ahead of time, then we built our musical system. Now it's time to finish this part of the patch by adding an octave offset. So this is a little more complicated than I would like, but not too bad. So we should be in pretty good shape. I'm going to do the octave offset here when we're working with a MIDI note number. That gives us the ability to work with an integer and much easier to work with as far as a frequency. So if we need to go up an octave, it's just a number 12, right? 12 semitones. We add those integers to the MIDI stream coming in, and we've transposed the note up 12 semitones. So our oscillator would be at a higher octave. So I'm going to do that here by adding or subtracting integers. So let's we're going to drag from here, and we want a add. So there's an add integer, and we'll connect our original MIDI note back up to the top. Okay. And then we really want to have a input for oscillator 1. And I'm going to call it octave. Technically, we can change lots of things, but this would typically be an octave knob on a Moog synthesizer. So oscillator 1 octave is what this is. This is an input pin. Now, I really wanted it to be a dial, right? But the problem here is that this is a an integer output. We talked about that earlier with this input being an integer and so on, and having conversions. And now we do have to do a conversion, for better, for worse. The problem with integer value streams right now in MetaSounds is we can't turn those into a dial input. So I actually have to convert this input from an integer to a float. So I'm going to convert that to a float. Now it turns into a dial as an input, and I have to rewire it and let that conversion of a float to integer take place here. And then the last step will be to have meaningful ranges. So I'm going to do -12 for the bottom. So we could go an octave down if we turned it all the way counterclockwise. And then I like going up 2 octaves perhaps on the top end. So as we adjust this knob, we'll be able to go down an octave or up 2 octaves from the default value. Okay, I'll clean this up really quickly. And it'd be nice if we could copy that and use that down here, but we need individual inputs, so copying those is not going to help me. So one more time, I need to come from this position, and I'm going to add an integer. And we're going to reconnect the top to this here, so the signal comes through for the note number. And then we want to promote to I made a mistake. Okay, we want to add an input graph here. We're going to rename this one oscillator 2 octave. Okay, and we need to convert that to a float. Okay, great. And then we attach it one more time for the conversion of float to integer so that we can use this knob. And isn't that fun? So we'll put in -12. And then we're going to put in 24 just as we did in the other one. And now we've got a octave controller for the center oscillator. And then I'm going to do that one last time here. And we're almost done with our patch. So add. Great. We'll reconnect the MIDI note. We'll take this and we want to promote to the graph input. We're going to name this oscillator 3, our last oscillator, and that's our octave control. And then from this we want to convert to a float. Okay, and then I'll reconnect here. And I'll change my range again to a meaningful range. And 24 here. Okay, great. So now we've got octave control for each of our 3 oscillators. Okay, so let's test that really quickly. I'll play the sequence again. Okay, and I'm going to move this one to an octave above. Great. Clearly I can hear that change taking place. Okay, and then I'll move this one to an octave below to make sure that's working. Yep, and clearly that one is working. So you'll have to play around with your detuning depending on which way you've gone with up or down octave. You'll need more or less detuning when that's appropriate. But we've got the basic controls here for an excellent synth patch. And again, I'm really thrilled that we're able to find all the tools necessary to make this possible. We've got a few workarounds that were necessary to use these in a more traditional way, but everything's working as we really need it so far. So I think it's really important that we have reverberation for electronic instruments. Electronic instruments don't have a resonant body the way traditional physical instruments do. Anytime I pick up an acoustic guitar or even an electric guitar and an amplifier, it's just about impossible to avoid some kind of room resonance. And that is not a problem. I think it's something that we really need to incorporate into the instrument design. So some people take an approach that reverb is something we only add in the final stages of the mix process. I think it can be an integral part to the actual instrument design. Some of my favorite synthesizers have spring reverb built in, and I'm always integrating them into a degree into the voice of the instrument itself. So we're going to go ahead and for the last step here, we're going to add reverb. And we got one reverb algorithm to work with, and that is going to be our this plate reverb. And it will give us stereo, and we should take advantage of that. It's a great way to start opening up the spatialization of the sound, make it feel like it's present in space. So I'm going to go ahead and convert this MetaSound to a stereo MetaSound instead of the mono. So I'm going to go to the MetaSound panel here, switch to stereo, and then I'm going to hook up our left and right outputs here to there. And we're going to do mono to stereo. So we're going to wire both of the mono inputs for our voice to both inputs here. And different reverb units or effects work a little differently in this regard. But in our case, wiring both of them, to me, seems to give the best result. I'm going to increase our decay time by decreasing this value here. And I'm going to go with something like that. And I'm going to make it a little bit brighter than the original default. The nice thing about this reverb is it does have an EQ already built in, so you're not fighting that really metallic sound we can get when too much high end is going into and out of the reverb. So, I'm going to boost it a little bit from the default. And I'm going to decrease the wet to much less. So I'm going to make that like 0.3 gain or 30% on the wet. So somewhere around in here, I found some pretty good results of the reverb. So let's try that again. So just enough to give us some flavor and a little bit of room sound to this voicing. And there you go. We've got our basic synth patch. To finish up the work, we could, taking up a little bit of more space than I like with all of this octave conversion, the detuning. But we'll go ahead and label this with a comment now. We're going to comment this one for our oscillators. Okay, there we go. We got our oscillators and our mixer. And we'll go ahead and do our mixer here. Okay, if you have followed along, you have now successfully created your own subtractive synthesis patch in MetaSounds. Again, I'm absolutely thrilled that we have these tools. I'm thrilled that I can create a convincing subtractive synthesis patch with a tool set that seems to have just fallen out of the heaven into Unreal just a few years ago, and we're able to take this so far. I can't wait for new tools like this to evolve and come to our palette. I can't wait for all types of new reverb, different types of filters, different types of sequencers that we might be able to integrate in this and really branch this out into a much more flexible system. For now, this is an excellent place to be, and I look forward to hearing what everybody else can make with these tools. Okay, I hope you've enjoyed this tutorial to build your own synthesizer patch in MetaSound. We've learned some basic synthesis methodology. You've learned to implement subtractive synthesis in MetaSounds. And more importantly, if you follow that last instruction, you can actually build your own subtractive synthesizer in MetaSounds, make your own adjustments, and create really powerful sounds to be used in Unreal in lots of different applications. So I think it's pretty important to recognize that MetaSounds has a huge range of really high quality synthesis modules. This hasn't happened overnight. Things have been progressively getting better, but it's really exciting to see that we can create a convincing synthesizer using these tools. And we are able to traditionally adapt this synthesis into MetaSounds, but it does require some creative solutions with the way that we work with certain aspects of the modules. It's really exciting to see harmonics tools opening up new doors to music creativity on Unreal. I think the sky's the limit of what we can do to create more musical interactivity with gameplay and other types of experiences. Thanks again for your time, and I hope that you join me for more tutorials in the future.